About 26 light-years away, a rocky world circles a faint red star in less than 2 days. The planet is called GJ486b. It is larger than Earth, heavier, and extremely hot. Surface temperatures approach 430 degrees Celsius, hot enough to melt metals. Under conditions like that, no stable atmosphere should survive. And yet, the James Webb Space Telescope detected something unexpected, a faint signal consistent with water vapor. But before jumping to conclusions, we need to slow down, because detecting water is not the same as finding an atmosphere, and finding a signal is not the same as proving its origin. Tonight we examine the science behind that detection. What was actually observed, what it might mean, and why the answer is still uncertain. GJ486 is a red dwarf star. Red dwarfs are small, cooler than our sun, and incredibly common. They make up nearly 70% of stars in the Milky Way. But they are not calm. They flare. They produce magnetic storms. Their surfaces are covered with star spots, cooler regions that alter their light spectrum. Understanding the star is just as important as understanding the planet, because when a planet transits its star, we are not just observing the planet. We are observing starlight filtered through complex stellar physics. GJ486b is classified as a super-Earth. It is about 1.3 to 1.5 times Earth's size. Its density suggests a rocky composition, iron core, silicate mantle. Gravity on its surface would be roughly 3 times stronger than on Earth. It orbits extremely close to its star, completing a full orbit every 1.47 days. That means it is almost certainly tidally locked. One side permanently faces the star, the other remains in darkness. This creates extreme thermal contrast, and such intense radiation should strip away any atmosphere over time, which is why this planet was originally expected to be airless. During transit, a small fraction of starlight passes through the region surrounding the planet. Webb splits that light into a spectrum. Different molecules absorb light at specific wavelengths. Water vapor absorbs strongly around 1.4 microns, and that is exactly where Webb detected a faint dip. The signal was tiny, only a few dozen parts per million, but it appeared in 2 separate transits. That makes random noise unlikely. The signal is real. But what produced it? There are 2 main possibilities. One, a planetary source. The planet could have a very thin atmosphere, not thick like Earth's, not even close, possibly only microbars of pressure. Volcanic activity could release water vapor from the interior. Tidal heating from its orbit could keep parts of the mantle molten. Outgassing might continuously replenish a fragile exosphere, but radiation from the star would constantly destroy water molecules. Hydrogen would escape into space. For vapor to persist, release and loss would need to balance precisely. It's possible, but challenging. 2 stellar source red dwarf stars can contain water vapor in their cooler surface regions. Star spots are cooler than surrounding areas. If the planet crosses over one of these spots during transit, the stellar water signature can mimic a planetary atmosphere. The effect is subtle and extremely difficult to distinguish. In fact, current data supports both explanations nearly equally. Roughly, 45% planetary, 55% stellar, within uncertainty margins. This is not just about one planet, it is about methodology. Rocky exoplanets are far harder to study than gas giants. Their signals are weaker. Their atmospheres thinner. If Webb can detect molecular signatures at this level, it proves the technology works. But it also proves something else. Stars are not simple light bulbs. They are chemically complex. Future studies must model stellar contamination with extreme precision. Otherwise, we risk misinterpreting data. Webb will observe additional transits using different instruments, specifically NIRISS, which covers a slightly different wavelength range. Here's the key test. Planetary water absorption weakens at shorter wavelengths. Stellar water absorption strengthens. Measuring the slope of the feature across wavelengths will determine the source. This requires extreme calibration accuracy, thermal drift in the telescope, detector gain variation, stellar variability. Everything must be accounted for. Only when all data sets converge will scientists declare a definitive answer. If the signal is planetary, it proves that even extremely hot super-Earths can retain trace atmospheres. That changes models of atmospheric escape. If the signal is stellar, it improves our understanding of red dwarf photospheres. And that is equally valuable. Either way, the result advances exoplanet science. Conclusion. Right now, the truth remains unresolved. A faint absorption line. Two possible origins, planet or star. But this is how science works, not through dramatic declarations, but through careful elimination of uncertainty. 26 light-years away, a rocky world continues its rapid orbit, and each photon arriving here carries information waiting to be decoded. The universe rarely gives simple answers, but it always rewards careful observation. If you enjoyed the video content, don't forget to like and subscribe, and let the information come to you. Welcome to Science Nucleus, where we explore the core of reality.